All right. Now this is lecture 14, part 2, more on equivalence relations. Okay. So first of all, a few announcements regarding homework. It's important to give yourself enough time to think about the material, and the suggestion is to try to work on a problem, some of the problem once a day, and then try to use T office hours, and try not to try to solve all assignments all at once, and it sometimes takes much longer than you expected. And in general, there's also additional instructions we listed over Canvas, and it's important to keep in mind to try to solve homework problems. Number one is to read the relevant chapters in a timely manner. Two is to try to do some of those practice problems. And also there's blue problems at the end of the textbook, which come with solutions. So you should try to solve this on your own. And if you are struggling, there's also additional online activities on the textbook website. And if you're still struggling with homework, with those steps, please come to office hours, and then use Piazza to pose questions. All right, so I want to make a quick correction. In recitation 7, I used the definition of a composition that is actually not consistent with the definition of the composition relation that is from the textbook. In fact, both definitions can appear in various areas, but in the textbook, they have a different definition. So, so we're going to revisit this question again and try to stay consistent. So in the textbook, if you have a relation R with domain A and codomain B, and a relation S with domain B and codomain C, we can define the composition of relation S and R. So if you think about a mental picture, you have a relation R that goes from domain A to codomain B. You have a relation S goes from domain B to codomain C. Then you have a composition of relation going from domain A to codomain C. And in the textbook, it's actually denoted of R first and then S. So in a way that is actually the first relation is R, and the second relation is S. In recitation 7, the same thing, I was using R and S, and then this definition is still correct in many different places, but it's not consistent with the book. We are going to go with the notation from the textbook because this is also consistent with the composition of a function. For example, if I have a function from x to y and function g from y to z, then the composition of f to g goes the first piece first. F comes to the right-hand side, g goes to the left-hand side, is from domain x to codomain z. Okay, so this notation that I'm introducing here, which is consistent with the textbook, is also consistent with the composition of functions. Okay, so now if we go back to the problem from recitation 7, we need to make a small correction in the actual proof using this new definition that is consistent with the textbook. So again, if you have a relation from A to B, and a relation from B to C, and a relation from C to D, we want to prove that this kind of ordering of a composition is equivalent. So it's a minor modification from the proof we had from recitation 7. Okay, so in this case, what we want to show in part 1 is we want to show the left-hand side is a subset of the right-hand side. All right. So if you look at here, a relation AC belongs to SR, where R comes first and S second in terms of the composition, as shown in the picture, if there's an element B such that AB is in R and BC is in S. So this is the same. I have A, I have B, I have C, and I have a relation go from A to B and B to C. Okay. So now how do we prove this? Is now suppose we have AD that belongs to the left-hand side. So what does this mean? This means there exists an element B that is in such that A of B belongs to T and B of D belongs to R composed with S. And because B of D belongs to here, this means there exists C such that B of C belongs to S and C over D belongs to R. Because we have both AB is in T and BC is in S, this implies AC can be in the S composed with T. All right. And because AC is in S composed with T and CD is in R, we have AD now belongs to R composed with S and T, which is the right-hand side. So therefore we have left-hand side is a subset of the right-hand side. All right. So this is a sketch of the first part, and the second part is similar. So this is a detail of the proof. Okay. So now we are going to review some problems relating to prove relations, the property of relations. So you could pause the video right now and try to solve this in 2 minutes. Okay. So this problem is asking you to prove if there's any relation R that is on a set A. So R again is a subset of A cross A. If R is transitive, then R composed with R is a subset. Of R. Okay. So again, what we could do is to review mathematically what is the definition of a composition, as we just saw. So, and if R is a relation from defined on domain X to codomain Y, and S is a relation from domain Y to codomain Z. So those are two binary relations. Then their composition which is S composed with R, is the relation S composed with R, where element XZ is in with the domain X, codomain Z, if there exists Y in the codomain Y for R and domain Y for S, such that XY is in R and YZ is in S. Okay, so that is sort of rewriting the composition of relation in this form. Okay, so now let's focus on the proof of this. So if we want to do this, the hint is going to use element-wise proof. That is proof if AB is on the left-hand side, it's also element in the right-hand side. Okay, so sketch. Let AB to be an element of R composed with R. By the definition of composition of relations, there exists C such that AC is in R and CB is in R. Okay? Because we have this two, since R is transitive, and we have AC is in R and CB is in R, this implies by transitivity, AB is in R. So that's it. That's the end of the proof. We start with AB, that is an element from R composed with R. We end up showing that it's an element in R. So the left-hand side is a subset of the right-hand side. Okay. Now let's do a quick review of how to prove a relation is antisymmetric. One way to prove it is to start by saying that we have a pair of elements from my set such that AB is in R and BA is in R. And we're going to use the definition of R to conclude that the only time AB is in R and BA is in R is when A is equal to B. Okay. If we want to prove a relation is symmetric, then what we need to do is we start with assuming for any pair AB is in R, and through some definition of the relation, we want to arrive at the conclusion that BA is in R. Okay. And let's also review some other type of orders. Remember, a relation is partial order if it's antisymmetric, transitive, and reflexive. And again, the easy way to remember is RAT or RAT. A relation is strictly partial ordering if it's antisymmetric, transitive, and irreflexive. So I or IR, depends on how you want to remember this. But of course, in actual exams, please spell out the actual words itself. So a relation is total ordering if it's a partial order, and for any element in the set, if they're not equal, either AB is in the relation or BA in the relation. In other words, that it's a total ordering. That means every pair of elements, distinct elements, are essentially comparable. And finally, the strict total ordering, asking for the same kind of requirement, except that it's replacing antisymmetry from the partial order by, it's replacing reflexive definition in the partial order by irreflexive. All right. Okay, so now let's recall what is a different requirement of a set partition. And this is where you can pause the video and try to recall on this piece of paper here. So there's three requirements. If you have a set partition by subset Si, the first thing is that for any element in your partition, it's non-empty. The second is for any pair of elements that their intersection is empty. And the last one is if I have n partitions, the union is equal to the domain, which is a set. So this is what's spelled out in detail. Okay. All right, now we recall the definition of an equivalence relation. If you have a set A and a relation on R on A, the relation is an equivalence relation if there's a partition of A such that for every pair in the relation, if and only if the elements are in the same part of S. Okay, so that's equivalence relation. And now if you have relations, there is several properties. The relation is reflexive. Sometimes use letter R for abbreviation in this lecture. If A and A is in the relation for any A. It's symmetric if AB is in R implies BA is in R. And transitive if whenever AB is in R, BC is in R, then AC is in R. And an important part that we're going to use a lot to prove a relation is equivalence relation, if and only if it is reflexive, symmetric, and transitive. RST. Okay, so you're going to use this theorem quite a bit when you want to prove a relation is an equivalence relation. So now let's look at a problem, right? I have A squared minus B squared is divisible by 5 as a way to define element in the relation T. So let's look at what might be in the T. So for example, 1 and 1 is in T, right? Because 1 squared minus 1 is 0. And that is divisible by 5. Maybe 1, 4 is in T, because 1 squared minus 4 squared is minus 15, which is also divisible by 5. And of course, 4 and 1 should be there too, because 16 minus 1 is 15, which is divisible by 5, and so on. So I'm listing this element just to give myself a guidance to say what type of elements belongs to this relation. All right, so we want to prove it to be an equivalence relation. We want to essentially prove it's reflexive, symmetric, and transitive. Those are the 3 things. So we're using the theorem we just reviewed. You know, a relation is equivalence relation if it's reflexive, symmetric, and transitive. So now let's show, you know, T is reflexive. I'm just using abbreviations right here. So I will start with an element that is integer. We want to show A and A is in there. But if I A squared minus A squared is equal to 0, which is 5 times 0, that means it is divisible by 5. Therefore, A of A is in this relation. Number 2, we want to show this relation is symmetric. So if you want to show it's symmetric, you start with a pair AB that is in the relation. Any pair AB that is in relation, you want to show BA is also in the relation. Because AB is in relation, we have A squared minus B squared is equal to 5K, right? That is by definition. And if I do some manipulations by multiplying minus 1 on both sides, this gives me B squared minus A squared is equal to 5 times minus K. Because K is in integer, that means minus K is also integer. So that means B squared minus A squared is 5 times some integer. This implies B of A is in this relation. And finally, we of course want to show the relation T, as the relation T is transitive. Okay, I'm using T with a circle to abbreviate transitivity. So again, what we have is we're going to let a pair AB that is in the relation T, and another pair BC is in the relation. We eventually want to show that AC is in the relation. Again, we're just going to use the definition of this relation. which is a squared minus b squared, is divisible by 5. Because AB is in the relation, that means a squared minus b squared is equal to 5 times p for some integer p. Similarly, b squared minus c squared is 5q for some integer q. All right, so everything I'm saying here is a sketch. Now, only thing I need to do is to arrive at a squared minus c squared. What we need to do is to add those two equations together. I get a squared minus b squared plus b squared minus c squared, which is equal to a squared minus c squared. Okay, I'm running out of space. I'm going to continue right here. So I have a squared minus c squared is equal to 5 times p plus 5 times q is equal to 5 times p plus q. Because both p and q are integer, by closure property of integer, p plus q is also integer. So this means that a squared minus c squared is equal to 5 times some integer. That means it is divisible by 5. So this implies a and c is part of the relation T. So now I have shown that relation T is reflexive, symmetric, and transitive. Therefore, it is an equivalence relation. That is the end of the proof. Okay. So now we want to prove if a relation R is symmetric, then this relation is equal to its inverse. So of course, if you think about a relation, it's a set of, if it's a binary relation, it's a set of pairs. So in order to show that those two relations is equal, we just want to show, number one, left-hand side is a subset of the right-hand side, and number two, you want to show the right-hand side is a subset of left-hand side. Okay. So, but before we do that, let's recall the definition of an inverse. Okay. So what is the definition of an inverse? So if we are giving a relation R with domain A and codomain B, the relation R inverse, it has a domain B and codomain A is the inverse of R, and it is defined so that x, y is in R if and only if y of x is in R inverse. So that's the definition of R inverse. Okay, so now let's get back to the proof. In order to show R is a subset of R inverse, we're going to start with an element that belongs to R and show that it is part of R inverse. So let AB belongs to R. Okay. Now, by definition, of R inverse, AB is in R if and only if BA is in R inverse. And because well, actually, we're using this too quickly. Let's start from beginning. If I start with AB is in R, because R is symmetric, we have B of A is also in R, right? This is just using symmetric property of R. And now we are using definition of R inverse. We have, because BA is in R, if and only if AB is in R inverse. So we start with AB is in R. We arrive at AB is in R inverse. Then we have R is a subset of R inverse. Okay. The second part is we start with element is in R inverse. Now, by definition of R inverse, we start with element here. And now, again, we're going to use symmetry again first. Because R is symmetric, we have, again, B of A is, well, no, hold on, apologies. We are going to use the definition of R inverse first. So by definition of R inverse, AB is in R inverse if and only if BA is in R. And now I'm going to use symmetry. Since R is symmetric, since BA is in R, we have AB is also in R. So again, we start with AB is in R inverse. We arrive at AB is in R. That means the left-hand side is a subset of the right-hand side. Okay. So now I proved both part 1 and part 2. And combined, we know that those two set R is equal to R inverse. Okay. Now the next question is that if I give you a relation, which is defined that x, y is in the relation if their difference is divisible by 3, we're going to ask, is this R an equivalence relation? Okay, and correspondingly, we're going to ask, what is a partition that is induced by this equivalence relation? So again, if you think about equivalence relations, what you need to think about is, does it satisfy a few properties? Does it satisfy being reflexive and symmetric and transitive? That is how you decide whether a relation is equivalence relation. So let's do this separately. Okay, so what is the problem here? The problem is you have x minus 1 is divisible by 3, and A is a set that is from 0, contains 7 elements from 0 to 6. Oh, that's not what I want. Just write it right here. My set A is from 0, 1, 2 to 6. And the relation R is xy such that x minus y is divisible by 3. Okay. We need to check, is this relation reflexive, symmetric, or transitive? So to show something that is reflexive, if we start with the element A that is in my set A, we want to show that the pair AA is part of the relation. Okay. Let's recall this question one more time. Sorry, it's divisible by 3. Yeah. Okay. So now what do we have? I take A minus A is equal to 0, which is 0 times 3. So it's divisible by 3. So we have A of A is part of relation. So this is relation is reflexive. Now, if I want to show it's symmetric, I'm going to start with a pair that is in a relation, and we want to show pair AB is in there, and then the pair BA is in there. So what do we have? If A minus B is in the relation, that means AB is in the relation, that means A minus B is divisible by 3. This is easy. If I multiply -1 by both sides, I have B minus A is equal to 3 times minus K. Because K is an integer, we have minus K is also an integer. So this means B of A is in R, right? Everything I'm writing here is again a sketch. Finally, if I want to show if this is transitive, I have a pair AB is in R and BC is in R, and we want to show AC is in R. Because AB is in R, we have A minus B is equal to 3K. BC is in R, that means B minus C is equal to 3M, where both K and M are integers. I can simply add those two together. I have A minus B plus B minus C, which is equal to A minus C is equal to 3K plus 3M, and 3 times K plus M. Because K is integer, M is integer, by closure property, K plus M is also integer. So therefore, A minus C is divisible by 3, which means A and C is a pair of each relation. Okay? All right. Now, the next thing we have to solve is, now we show that this is equivalence relation. What is a partition induced by this equivalence relation? We can start with, say, element 0. What is in the same set with element 0? So let's say this is my partition. If 0, the difference between 0 and 3 is divisible by 3. So 3 is in the same set. Similarly, difference between 0 and 6 is divisible by 3. Okay? And that's it. Now let's start with element 1. Which element, the difference between 1 is divisible by 3? It's 4. Okay? And now let's start with 2. 2 and 5, because their difference is divisible by 3. So this is actually the partition. Of course, you can check the property of a partition. Right? What is the property? Number 1, neither of those set is empty. This is S1, S2, S3. Number 2, for two things that is not the same, their intersection is empty. And number 3, the union is equal to my set. Okay, so this is a partition induced by the equivalence relation. All right. So now let's look at a new problem. We started the divides relation on positive integer. So this means positive integer. A pair of positive integer is in the relation. So AB is in the relation if and only if A divides B, right? So now we want to show it's a partial order on the positive integer. When you think about partial order, you need to prove something is partial order if it's reflexive, antisymmetric, and transitive. Those are the 3 properties you want to show. Okay, so I want to show, let's see if it's reflexive. Okay, remember reflexive, I'm going to start with an element that is positive integer. And we want to show AA is in this relation. Okay. So what do I have? Because A is equal to 1 copy of A, therefore A divides itself. This implies the pair AA is in the relation, so the relation is reflexive. Okay, so that's good. Now, next thing I want to show, it is antisymmetric. First of all, let's check if it's antisymmetric. For example, if I have a number A is equal to 2, number B is equal to 4, we know that AB is in R because 2 divides 4. However, B of A is not in the relation because 4 does not divide 2. Okay, so this is a check, but not a proof. So I now need to write out the proof. If I want to show something is antisymmetric, then suppose A and B is in R and B and A is in R. We want to show the only time both of those relations are in the set is when A is equal to B. So that is how you prove something is antisymmetric. Because A, B is in R, we implies A divides B, which means B is equal to A times some integer K. Because BA is also in the relation, we have B divides A, which means A is equal to B times some integer M. So now I have B is equal to AK and A is equal to BM. We can say by substitution, A is equal to B times M, which is equal to AK times M, which is equal to A times KM. Okay. And because A is bigger than 0, which is positive, we have Km is equal to 1. This implies K is equal to 1 and M is equal to 1. Let's add another page. So Km equal to 1 implies K is equal to M, 1, M equal to 1. So this implies A is equal to B. So that is a proof for the relation being antisymmetric. Next thing I want to show if this relation is transitive. So suppose we have AB that is in the relation and BC is in the relation. We want to show AC is in the relation. Because AB is a relation, we know that this implies A divides B. That means B is equal to K times A for some K. And BC is in the relation, that implies B divides C. That means C is equal to M copies of B, where M is integer. Now, in order to show AC is in the relation, we just need to show that A divides C. So we can just use substitution. C is equal to MB. Substitute B is equal to M times K times A, which is A times KM. Because K and M are both integer, then by closure property of integer under multiplication, K of M is part of the integer, is an integer. So now C is A times some integer. This means C divides A. It means A divides C, which implies AC is part of the relation. So now I have showed this relation is reflexive, antisymmetric, and transitive. it means that this is a partial order, right? Okay. Finally, we have one last question. Is considered relation where AB is in a relation when A plus B is odd. So we're going to ask, what property does it have? So this is the same thing where in order to ask a property, we're going to ask, is this reflexive? Is this symmetric? And is this transitive? Okay. So first of all, is this reflexive? So when I say when AB is in odd in the relation, let's look at what possible elements do I have. For example, 1, 2 is part of the relation because 1 plus 2 is equal to odd. 1, 1 is not in the relation because 1 plus 1 is equal to 2, okay, which is even. Maybe 2 and 3 is in the relation because 2 plus 3 equal to 5, that's odd. And minus 1, 2 is also part of the relation because their sum is equal to 1, which is odd, and so on and so forth. So this gives you some hint about what sort of property do you have. So let's now check. As I mentioned, 1 and 1 is not in this relation, which means that, you know, it's not reflexive, okay? Why? You know, if suppose R is reflexive, that means A and A is in R. However, A plus A is equal to 2 times A, and where A is integer, this implies, well, not say implies, this means A plus A is even, which does not satisfy the condition of the definition of R, right? So this is a contradiction that AA is in R. Okay, so this here is just a quick proof. Now, is this symmetric? Okay, so if we start with AB is in the relation, we want to show or not shown or show that it's not true, B of A is equal to this, is also in this relation. Because AB is in this relation, that means A plus B is equal to odd, which means it's equal to 2k plus 1 for some integer k. By just doing swap between A and B, it means B plus A is also equal to 2k plus 1, where k is integer. So this implies that B plus A equal to odd number. That means B and A is in this relation. So far what we have is we know that it is not reflexive, but it is symmetric. And finally, we want to ask, is this relation transitive? Okay, so again, I'm going to add extra page. So is this relation transitive? Let's say we have AC is in the relation and AB is in a relation and BC is in a relation. The question is AC in a relation? Okay. Since AB is in the relation, the definition is A plus B has to be odd. So A plus B is 2n plus 1 for some n that is integer. And also, since BC is in a relation, then B plus C is equal to some odd number, which is 2k plus 1 for some k. Now we need to know what happens to with A plus C, okay? So then what is happening with A plus C? How do I get to A plus C? I add those two together. On the left-hand side, I have A plus B plus B plus C. On the right-hand side is 2n plus 1 plus 2k plus 1. And now I do some multiplication. I have A plus C plus 2b is equal to 2 times n plus k plus 1. Minus 2b on both sides. So I have A plus C is equal to 2 times n plus k plus 1 minus b. We know that n is integer, k is integer, and b is integer. By integer closure property, this is integer. So now A plus C is equal to 2 times some integer. By closure property of integer. That means A plus C is even, which means AC is not part of the relation. So this relation is not transitive. All right. So if I go back to the problem, it is not reflexive, it is symmetric, and finally, it's not transitive. Okay. So that is for today. Have a good rest of the day, and I'll see you next week.